All right, this is the last video in this Lecture 2 series. So I just want to look at a couple of results with you. I'm not going to work out hardly any examples. It's just important that you at least have heard of some of the different theory. So first corollary, if f is analytic on a domain D, then its derivatives of all orders are analytic on D2. Keep in mind the difference between having a formula for a derivative and being analytic. Analytic means that you are given any point inside D, then your derivative exists on a little neighborhood of that point D. And so this corollary follows relatively easy from Cauchy's generalized integral formula. I would encourage you to pause the video for a moment and see if you can see the connection and see why it's true. There's some theory behind it. You can read the book for more details. But I did want to make a remark with you before we go on and look at some other results. And so the point is that this result is not true over the reals. And I thought it would be nice to have a counterexample for you. So let's look at f of x equals x to the 5/3. This function is differentiable on R. It's differentiable everywhere. And so you can take its first derivative. And so let's do that. Let me not show you too much of what's to come. So f prime of x in this case is what? 5/3 x to the 2/3. Certainly its derivative, this guy exists and is continuous everywhere on R. Okay, but if we do it again, if we compute f double prime, then all of a sudden I get what? 10/9 x to the minus 1/3, and the second derivative does not exist when x is 0, right? So even though you have a function that's differentiable everywhere, its derivative exists everywhere on the reals, here if you take enough derivatives, in this case the second derivative, then there's a point where the second derivative doesn't exist. And so this corollary 1 is special to the complex, to functions over the complex plane. All right, so that's that. Next corollary was kind of popping at the bottom of the screen below. Hopefully it wasn't too distracting. So if I can think of my function as u of xy plus I v of xy, if f defined as u plus iv is analytic on a domain D, then u and v have continuous partials of all orders on D. And you can see how that follows from the previous corollary. All right, I want to look at another theorem with you, and I just realized I forgot to look up how to pronounce his name. I've forgotten it. It's been years since I've looked at it. Hopefully I'll get it right. Before we look at Morera's theorem, I think that's how you say it, I want to recall the Cauchy-Gaussat theorem for simply connected domains. In the last video series I didn't label this theorem with this label, and I wish I would have. I did when I typed up the notes. The problem with all of these theorems is it becomes difficult to keep track of them. So I'm trying to give as many of them clear names as I can. So the Cauchy-Gaussat theorem for simply connected domains. F is analytic throughout a simply connected domain D, then the integral of f over c is 0 for every closed contour lying in D. Okay, so I want you to look at the next theorem with me and think of it as a sort of converse to the Cauchy-Gaussat theorem for simply connected domains. So here it is, Morera's theorem. If f is continuous on a domain D, let's assume that f is continuous on a domain D, and if every integral of f over a closed contour is 0 for closed contours lying in D, then f is actually analytic on D. So it's sort of a converse. So here, if f is analytic, then every integral is 0. If every integral is 0, then F is analytic. That's the idea. My battery is fading faster. Hopefully we can finish this. So yeah, as I said before, you can think of this as a sort of converse to the Cauchy-Gaursat theorem for simply connected domains. Last thing I want to show you, last result. This is Liouville's theorem. So if F is entire, meaning it's analytic on the complex plane and it's bounded, then it's constant. So that's a really nice result to know. The only functions that are bounded, meaning bounded everywhere, meaning their value, the modulus of their value is always less than or equal to some constant. If F is bounded on the complex plane and it's analytic everywhere, then F is actually constant. So again, this course, we're thinking more computational, less theoretical, but I just couldn't help but mention this result. It's so useful in so many things. And then finally, last remark, the fundamental theorem of algebra that you've learned since you were a wee child follows easily as a corollary from Liouville's theorem. Let's remind ourselves what it says. I won't write it, but it says every polynomial of degree at least 1, let's say it has degree n, then every polynomial of degree n at least 1 has n zeros if you're counting multiplicity over the complexes. So polynomials over the complex plane all factor into linear factors. And you can use Liouville's theorem to prove that result that you've known for a long time very easily. All right, so I will stop here, and you can look on the homework list in Teams to get the homework problems. We've covered several sections, and so I'll assign you the homework, and I'll also say when it's due on our file.